Hi folks. Today we're going to look at actually factoring some polynomials. So we'd spent 2 days on dividing, both using long division and synthetic division, but maybe we should remember our goal. What we want to do in this chapter is be able to graph complicated polynomial functions, and the sort of hack to doing that is to convert them to factored form. Once we do that, we can find the axis intercepts. It'll be easy to find the x-intercepts from factored form. And we can consider the end behavior of the graph. If it's odd and positive, we know that it looks kind of like this. If it's odd and negative, it looks like this one. Even and positive like this. Even and negative like this. And we came up with a dance that would help us remember these characteristics. So just to peer a little bit into the future, if we could get stuff factored, then we could learn the x-intercepts. If I had, say, this graph over here, I would learn that it has x-intercepts at 3 from this one, at -1, at -5, and +2. Those are all the numbers that would zero out each of the brackets. I would know that this graph has a highest power of 4 because x times x times x times x is 4. So this is even degree, or 4. It has a positive leading coefficient. I could do the dance and find out that it has kind of this basic shape. It goes from up to up. So if I just wanted to sketch it real quick, I probably could. Here's an x-intercept at -5, x-intercept at -1, x-intercept at 2, and an x-intercept of 3. And I would know that it starts from up here, comes down. Try and do this as smoothly as possible. Something like that. I bet you if you go to Desmos and graph this function, it'll have something approximating that behavior. Where exactly the max and min points are, I'm not entirely sure. That'll be the job of calculus, but it's a pretty good sketch for the graph. Similarly, we could take a look at this one down here. It would have x-intercepts at -5, -1, and 2. This one would be, let's see, x times x times x. That would be degree 3. So it would be an odd degree. And notice it has a negative leading coefficient. Okay? So odd and negative has this kind of look. It goes from up to down. I could sketch it pretty easily if I had it in this form. There are my x-intercepts. And I'll just give it this basic look. And again, I don't know exactly where its max and min are, but that gives me a general sense of the look of the graph. And again, I could verify that with Desmos. The question that remains is how do we get it into that form? And the answer is by factoring, and we'll use division to help us do that. So today we'll determine whether a binomial is a factor of some polynomial, and we'll factor some polynomials of degree 3 and higher. Here begin the actual notes from the section. This is the factor theorem. It's actually building on something called the remainder theorem, which we cut out from the curriculum this year, but you could check it out in the Chapter 3 Concept Roundup video. The basic idea is this. X minus a is some binomial factor of some polynomial, p of x. This is just some polynomial that we'll deal with. If and only if p of a equals 0, meaning if you throw in the number, it will actually give you a 0, because that's what a factor does. It's going to give you an x-intercept or a y value of 0. So if I want to check whether some binomials are factors of this polynomial right here, I can check it just by throwing in numbers. If I want to check x minus 2 to see if it is a factor of this polynomial, let's call this p of x over here, then we're going to throw in or put in 2 for x and see if it gives us 0. And see if we get 0. So let me check it out. When we say p of 2, that just means putting in 2 for x in this entire polynomial. See what happens. 2 cubed minus 2 times 2 squared. It's looking pretty good so far. Minus 11 times 2 Okay, so that's 8 minus 22 plus 12 is negative 10. Honestly, at this stage right here, I don't even care what the number is. I can see it's not going to be 0. And if it's not 0, that means that we don't have a factor. So what we just learned here is x minus 2 is not a factor. We can put a sad face. Let's check the other one. Check x plus 3. Now to do that, we would put in negative 3. Put in negative 3 for x and see if we get 0. Okay, let's see what happens. So same polynomial. If I put in negative 3, I would have, you can see it up at the top there, negative 3 cubed minus 2 times negative 3 squared minus 11 times negative 3 plus 12. Let's see what happens now. So that would be negative 27 minus 2 times 9 plus 33 plus 12, or negative 27 minus 18 plus 33 plus 12. Is that 0? That's negative 55 plus 55. Oh my gosh. We just found our first polynomial factor. X plus 3 is a factor of this polynomial. Now, if you were to think back to some questions that we had from the other day, we looked at factoring some polynomial, and we realized there were two big questions. How do we know when we have a factor? I think we've answered that question now. When it gives you a 0, you've found a factor. Once we know that we've found a factor, how do we know what's left over? And the answer to that was what we spent the last 2 days doing. It's through division. So now that we know that x plus 3 is a factor of this polynomial, we can use division to help us factor the polynomial. Just like if you learned that 2 was a factor of 18, you could go, oh, let me take 18 and divide it by 2. And you'd find out it's 9. So you'd learn that 18 is 2 times 9. And then you could factor it some more. You could factor that 9 into 2 times 3, and you'd get the prime factorization of 18. Same kind of process is going to happen here. To recap from what we just found, we found that p of negative 3 equals 0. Therefore, x plus 3 was a factor. That's what happened in the last question. Now we're going to divide. I'm going to take the whole polynomial and divide it by x plus 3. 2x squared minus 11x plus 12. You can do this with synthetic division if you prefer. I just want to make sure that it's clear what exactly it is we're doing. So I'm going to divide these out. X cubed divided by x is x squared. Multiply it back in. I get x cubed plus 3x squared. Carefully subtract. Okay, divide out again. I'll get negative 5x. Multiply it back in. Negative 5x squared minus 15x. Carefully subtract. That's going to give me 4x plus 12. Okay, divide them out. I get 4. And here's the thing. If you've found a factor, then necessarily the remainder is going to be 0. So what we learn is that if you take that big polynomial and divide it by x plus 3, you get x squared minus 5x plus 4. Or if I were to write that a slightly different way, what we now know is that x cubed minus 2x squared minus 11x plus 12 is the same as x plus 3 times x squared minus 5x plus 4, right? In the same way that when you find out that 18 divided by 2 gives you 9, what you really learned is 18 is 2 times 9. When we did this division, we learned a way to rewrite that big, ugly polynomial. And now that you've got it factored a bit, well, you can't help yourself. You just got to factor some more. Okay, so this is a short trinomial. We could go ahead and factor it using this long division stuff again, but that would be overkill here. We're just looking for numbers that add to -5 and multiply to 4. No big deal. Those numbers are -4 and -1. And there is the factorization of this big, ugly cubic that we started with. Now you can write those binomial factors in any order. It doesn't matter. Okay, let's do another one. We're going to verify that x plus 1 is a factor of this cubic, and then we're actually going to factor the thing down to its binomial components. So if we want to find out if x plus 1 is a factor, we need to throw -1 into that polynomial and see if we get 0. So that's -1 minus 4 minus 1 plus 6. Oh my gosh. I'm going to write it with an exclamation point. X plus 1 is a factor. That's what we learned by getting this result of 0 over here. If it had been anything other than 0, x plus 1 would not be a factor, and we'd have to hunting for factors, or we'd keep on having to hunt for factors. All right, once we figure that out, we know what it's safe to divide that cubic by. It's safe to divide it by x plus 1, and you should not end up with any remainder. So I'll divide it out, and then I'll do it synthetically afterwards, just to show you if you want to save yourself some steps. X squared is going to give us x cubed plus x squared. Carefully subtract. Get -5x squared. Bring a term down. Divide. -5x squared minus 5x. Okay, carefully subtract. Gives me 6x. Bring a term down. Oh, this is looking promising. I think I'm going to end up with no remainder. If I get a remainder, either I botched my division or I didn't really have a factor to begin with. For all that work, what we really learned here is that you can rewrite that cubic that you start with as x plus 1 by x squared minus 5x plus 6. And then you can factor some more if you really want to, which you should want to. If you see a short trinomial, you should just be overwhelmed with the urge to factor it. There's the prime factor, or not the prime factorization, the binomial factorization of that polynomial. Now, some of you are probably annoyed at having to use long division since we just spent yesterday trying to figure out how to do synthetic division. So if instead, after this point, you decided you wanted to go and use synthetic division, that would be absolutely fine. 1, -4, 1, and 6. Okay, I'd be dividing it by x plus 1, so I'd put a -1 here, and I'd put the times and plus to remind myself. And the steps would be 1, okay, -1 times 1 gives us -1, add them up, okay, multiply, add them up. Oh my gosh, remainder of 0. And from there, we learned the exact same thing, that x cubed minus 4x squared plus x plus 6 could be rewritten as x plus 1 times this quadratic that we just found here, 1x squared minus 5x plus 6. And then you could factor it even more. Same result either way. I think it's a little more opaque here. It's a little harder to see exactly what all these things mean. The process just looks like a bunch of numbers, but it is pretty fast. Alternately, if we do it with long division, you get to see the process all the way through. Whether you do it like I have it in red or in blue, doesn't matter. Same result either way. So that gives us two things. Number one, gives us some practice questions that we can do. On page 133, you could do 2 ACE, 3 ACE, and do 5 ABC, given that we know that these are factors. The other thing that you get from this work is a lingering question. And here it is. How do we know which factors to even try? In all the questions that I gave you today, it was given with a set of binomials to check out, and one of them happened to work. Here in question 5, I'm giving you some binomials to try that are going to be factors. But if you didn't have that insight or that information given to you, how would you know what's worth giving a go? That's the question that we'll deal with as soon as we get back in January, so I'll let it haunt you until then. I hope that you have a great break, folks, and take care. See you next year.